In this video, we will be discussing about the performance consideration in the memory system. In the earlier classes, we have discussed about the cache memory and three things that are being important factor while designing of the memory system are cost, speed, and size. So we need a very fast memory. We need a very large amount of memory with low cost. So key design objective of a computer system is to achieve the best possible performance at the lowest possible cost. Here's a price per performance ratio is a common measure of success. We want a better performance with low price. The performance of a processor depends on how fast machine instructions can be brought into the processor for execution. That means the instruction can be fetched with very fast technique, and how fast the instruction can be executed. How fast the instruction can be executed, the processor is responsible for the same. But how fast the instruction can be fetched to the processor. Now memory comes into act over here. So how this memory can be fetched from the memory modules. So see here, the entire memory is being divided into a number of modules. Each module contains a number of blocks, and each block has a number of words. So for example, the entire module may be divided into 128 entire memory may be divided into 128 number of modules. Each module may have a fixed number of blocks. Each block may have a fixed number of words. Now how these words can be placed in this module? There might be a chance the words may be stored from word 0 to word 100, word 100 to word 200, word 201 to 300, 301 to 400, like that it may be stored. And each module is having two registers. One is called the address buffer register and there is a data buffer register. So address that is being generated from the processor is first matched with this address buffer register, whether it is addressed is matched with this register or not. There is an address buffer register and data buffer register which contains the data to be written or read into from these modules. Now the address that is generated by the processor has two parts. One, to locate a module. Once a module is located, there are a number of words over here. Then some bits are used to find a word in this module. So two things are required. One is the module number, which module, from which module we want to read. Second one, once we got the select the module, which of word that is requested by the processor, that is given over here. This high order k bits, the high order k bits are used for memory address. This determines the module, and this determines what address in the module. This m bits, the low order m bits, decides a word in the module. Now what happens in this arrangement? The consecutive words are placed in a module. In a module means consecutive words, word 0, word 1, word 2, word 3, up to let one word 100 may be stored in one module. 101 to 200, all consecutive words are in next module. Like that it will be stored. High order k bits of memory address determines the module. So which module is determined by this k bits. And once the module is selected, the low order m bits of memory address determine the word within a module. Now suppose I want to read word 150 to 160. So 150 to 160 may be in the module number 2, and the module 2 is selected, and one by one the words are transferred from the same module. So out of number of modules, only one module may be busy in transferring the data. However, one word can be transferred at the same time, because after when the one word is sent to the data buffer register, the next word can be sent. So when a block of words is transferred from main memory to cache, only one module is busy at a time. However, there is an alternate method of arrangement of this memory. See here, Here also the memory is divided into number of modules. Here you have numbered as module 0 to module n minus 1. Here you have module 0 to module 2 to the power k minus 1. 2 to the power k minus 1, 2 to the power k, because it must be in 2 to the power k format. It may be 64, it may be 4, 16 to 4, 8, 16, 32, 64, 128, 256 in that way. So module 0 to module 2k 2 to the power k minus 1. Each module has address buffer register and data buffer register as it was there in the previous case. But here it says the consecutive words are located in consecutive modules. Consecutive words, if you have word 0 in module 0, word 1 is in module 1, word 2 in module 2, word 3 in module 3, word 4 maybe in module 4. So consecutive words are stored in consecutive modules. So now the high order m bits are used to address because there are multiple number of modules to be selected. Therefore, there are high order m bits are used to select the module, and low order k bits is used for selecting the word inside the module. A number of modules may be selected. But what happens over here? I want to read, suppose, word 150 to 160. 150 may be over here, 51 in the next one, 52 may be there. So next module likewise. So word 50 will be sent to the data buffer register of module 0. 151 word will be sent to data buffer register of module 1. Like that, 4 or 8 modules will send its data to its own data buffer register, and all will send the data from each of the modules. So data can be accessed parallelly, which could not be possible over here because all words belongs to the same module. So while transferring a block of data, several memory modules can be kept busy at the same time. So transferring rate is faster as compared to the first case. However, here only one module was busy, but here we have all the modules are busy at the same time. The second method of accessing this data is called the memory interleaving. The concept is called the memory interleaving. So we have parallel access to these modules, so that average rate of fetching words from main memory can be increased. So now we'll discuss about the hit rate and miss penalty. The hit rate says the number of cache hit divided by total number of access. So we may be accessing for number of times for reading or writing purpose to the cache, and some of them will be found in the cache. So total number of hits divided by total number of attempts give you the hit rate. Similarly, for the miss rate, total number of miss divided by number of attempts. But whenever there is a miss, if it is not found in the cache, we have to give the miss penalty. That means if the data is not found in the cache, we have to go to the main memory for fetching the information and put it into the cache. The extra time required to bring the data from the memory to the cache is known as the miss penalty. So more the miss penalty, our performance is lower. This hit rate can be improved by increasing the block size while keeping cache size constant. We may not increase the cache size. If you have increase in block size, many words may be kept in one block, the hit rate may be increased. The block size that are neither very small or nor very large gives best result. If you make very small size blocks, there might be a chance that more number of times the transfer may need to occur. If you make the block size very big, a substantial portion of the block may be unused. Miss penalty can be reduced if load through approach is used when loading new blocks into the cache. This miss penalty can be reduced if you go for load through approach. Load through approach is directly loading from the main memory. Load through approach is used when loading new blocks into the cache, so that the miss penalty can be reduced. Suppose I have a single label cache. What is the average access time? See here, I have a single level cache. So what I have processor, cache, and then the main memory. What is the average time it will take now for accessing from this cache? If H is the heat rate, C is the cache memory access time, and M is the miss penalty. H is the heat rate, means heat rate in the cache. So we access for number of times into the cache. Some are found. Those are found is the heat rate. So that heat rate is H. Once it is found, it can be transferred in C amount of time. C is the cache memory access time. So H is the heat, time to transfer is C. So what is the time to transfer from cache? H into C. So if H is the heat, what is the miss then? 1 minus H will give you the miss. Those data will be fetched from the main memory. And M is the miss penalty. So 1 minus H into M. So H is the heat rate in the cache it is found, amount of time it requires to transfer from the cache. So that is H into C. 1 minus S is the miss rate, number of miss, 1 minus S miss rate into the miss penalty, give you the average access time. In most of the cases, we have two-level cache. If you have two-level cache, what is the average access time? Here it says, the formula is H1 into C1. So heat rate in L1 cache into amount of time it takes to transfer from L1 cache. H1 into C1 plus 1 minus H1. What 1 minus H1 means? The information that are not found in L1 cache. Those will go to L2. Out of those, some are heat. Let H2 is the heat. So H2 is the heat out of this 1 minus H1. And amount of time it requires to transfer from L2 cache is let C2. So 1 minus H1 into H2 C2. So what is left now? 1 minus H1 into 1 minus H2. That means it is not found in L1 or L2. This will go to the main memory for access, and for which we have to give the miss penalty. So 1 minus H1 into 1 minus H2 into M. So if these values are given, then we can compute the average access time for a two-level cache. So what is the other performance enhancement? Here it says, for write buffer, we can use a write buffer here. The write buffer can be used for both for write through and write back. It says that each write operation involves writing to the main memory. If the processor has to wait for write operation to complete, it slows down the processor because the write operation takes much time. So what we can do, instead of the processor is waiting for the entire data to be written into the main memory, we can put it into the buffer only. So that the data can be put into the buffer and processor will go on doing some other tasks. Later this from the buffer, the data can be transferred to the memory. Similarly, in the write back also, the data can be put into this write buffer and it will go for reading the data. Block is written back if the processor waits for this write to complete before reading the new block, the slow down. Therefore, it will write into this write buffer and it can go for reading the data. Another way of improving the performance is by prefetching. The new data are brought into the processor when they are first needed. The data is usually not being brought to the cache if it is not required because of the locality of reference. But what we can do, whether it is required or not, if you can prefetch some data and put it in the cache, then some of the information may be found in the cache. So this process is known as the prefetching. The prefetching can be accomplished through software by including a special instruction in the machine language of the processor. So it can be done through the accomplished by the hardware also. There can be a circuitry which can attempt to discover pattern in the memory reference and prefetch accordingly. So it will find out a pattern that this may be required and put it in the cache. And next we'll go for the virtual memory.